Hi, I'm Seungeui Hong, and in this video, I will introduce you about qubits. Okay, first thing first. What is qubit? Qubit, quantum bit in other words, is the basic unit of quantum information. So from definition, we can see that qubit is quantum mechanical analog of classical bit. Since classical bits, by definition, is the basic unit of information in classic computers. So how are they different? The most important difference is that qubit can be in superposition of both states. Another difference is that measurement of qubit would destroy its coherence and irrevocably disturb superposition state, unlike in classical bits. Also, a unique phenomenon called quantum entanglement occurs in multiple qubits. Finally, one qubit can hold same or more amount of information than one classical bit. For example, using superdense coding, one qubit can hold up to 2 bits of information. Okay, this might not be very clear to you, but I will go over them one by one, so don't worry. Now, let's see how we represent a single pure qubit state. Again, the quantum state of a qubit can be represented by a linear superposition of its two orthonormal basis states, which are denoted as cat0 and cat1. These orthonormal basis states span the two-dimensional linear vector space of qubit. With two or more qubits, basis states can be combined. For example, two qubits are represented in a four-dimensional linear vector space spanned by cat00, cat01, cat10, and cat11. Then, how can you express the proposition in the pure qubit state? Coherence proposition of basis states can be expressed as cat psi equals to alpha cat0 plus beta cat1, where alpha and beta are complex numbers and satisfies this condition. Here, note that this expression does not mean that qubit have value in between 0 and 1. What this means is that the qubit has probability of square of alpha of the value 0 and probability of square beta of value 1. We will discuss it once more later in operation part. From the expression, we can assume that there are 4 degrees of freedom, since alpha and beta are complex numbers. However, using the constraint condition, we can eliminate 1 degree of freedom. Using one of coordinate system called Hopf coordinate, we can express alpha and beta with 3 degrees of freedom. And for single qubit, overall phase of state, e to the power of I psi has no physically observable consequences, so we can simplify the equation, leaving just 2 degrees of freedom, theta and psi. Therefore, quantum state of single qubit can be visualized using Bloch sphere, like shown in this image. Here, classical bit can only exist at North Pole cat0 and South Pole cat1, but qubit can exist at any point over the surface. Also, e to the power of I phi is physically significant factor, and it is called relative phase factor. Since we've seen how to represent qubits, let me introduce some physical operations that can be done on pure qubit states. First one is quantum logic gate, operating on small number of qubits. Qubits undergo reversible unitary transformation according to quantum logic gate. For single qubit, qubit factor will be rotated. For 2 qubits, specific quantum gate can entangle or disentangle them. We will talk about entanglement later. Here are some examples of quantum logic gates. The second one is standard basis measurement. It's an irreversible operation, gaining information of single qubit state and breaking coherence of it. To be specific, when we measure a qubit, the result will be either cat0 or cat1, with probability of square of alpha and square of beta, respectively. Then, magnitude of alpha and beta is changed. For example, if result is cat1, alpha will become 0 and beta will become e to the power of I phi, which is now inaccessible. So basically, when a qubit is measured, the superposition state collapses into basis state, and relative phase becomes inaccessible. Now let's move on to final property of qubits, which is quantum entanglement. It is non-local property of multiple qubits that allows them to exhibit higher correlation than in classical bits. Simply saying, in entangled qubits, if one qubit is measured, then other entangled qubit's value will be fixed. Bell state is the simplest example of quantum entanglement with two qubits, where it can be expressed like this. There are actually total 4 bases in Bell state, but let's just focus on this particular basis for this example. Here, since there only exists product state of cat00 and cat11, if one qubit's value is measured, then the other one would be fixed. Let's say that qubit A and qubit B is forming quantum entanglement in Bell state. Then, if we measured qubit A and got value of 0, then qubit B's value will be fixed to 0, even without measuring it. This relationship will always hold, even if these qubits are separated. This is the end of my video. I hope this video was helpful for understanding qubit and its properties. Thank you very much for watching this video.